Okay, so my name is Thierry Carrez. I'm the release manager for the OpenStack project. And today I'll talk about snakes on the cloud, or how we use Python to build open source cloud infrastructure software. Cloud. So there have been a number of presentations on cloud stuff already this week. So could you raise your hand if you have now a very precise idea of what cloud computing is? Okay. So for all the others, you probably think that a lot of different things are actually described as cloud. And the reason for this is that cloud is a buzzword. It's a very trendy buzzword, so if you have anything to sell, you should probably add the word cloud to it, like a presentation title. Works pretty well. And the thing is, cloud computing actually describes the transition for the computing industry from an industry of products to an industry of services. And the services that are born out of that transition share two main characteristics. One is ubiquity, so you can access the service from anywhere and from any device. And the other is elasticity, where the services are generally multi-tenant and you don't really have to care about the service scaling to meet your needs. And you usually pay for what you use exactly. But it started mostly with services that are geared towards end users, so with the software as a service. Salesforce started by hosting its CRM solution, offering a hosted platform for its CRM solution. Then there was Google Docs, and then almost every website that provides some kind of service would call itself cloud as well. So Gmail is cloud, Flickr is cloud, Remember the Milk is cloud, Twitter is cloud, and Facebook is cloud, and everything else is cloud too. And the other type of end-user services is online storage and streaming. So that's what Dropbox does, Amazon Cloud Drive, Ubuntu One, or the recently announced iCloud.
I add to the buzzword factor, I work on Ubuntu One, and the buzzword for us is personal.
Yeah, but you still use cloud icons, so that counts. I like this one. The other type of services that are born out of cloud computing are services that are geared towards system integrators, platform builders, or programmers. There is infrastructure as a service, which is about providing raw compute and storage resources. That's what Amazon Web Services does, but also Rackspace Cloud. And the other type of backend services is deployment platforms. So where you can basically upload your code and they will deploy it for you and scale it for you. That's what the Google App Engine, Heroku, EP.io, who are here this week, and Windows Azure usually do. Open source. That's an interesting problem. Where is open source in all this? So most of the services are actually using open source building blocks, but the software that they actually use to run their service is actually closed source. And the main reason for that is that they consider their code the secret sauce that enables them to prevent the competition from spinning an equivalent service with low cost. That said, some companies are starting to see the value of developing something in common rather than privately, separately. And the main driver for that is sharing development costs, obviously, but also the promise of creating a new standard and being part of that standard early on. So we're seeing more and more of that. And we should probably facilitate this. We should encourage that thinking, because for consumers of those services, it's really good to create competition, to eliminate vendor lock-in, which is one of the problems of cloud services, reducing, therefore, the barrier of adoption, and potentially enabling federation of equivalent services. That's where open source is really important in that space. So over the last year, we saw the emergence of 3 projects. There is Open Compute, that is pushed by Facebook to open source the hardware of data center design, the data center hardware design. There is OpenStack that promises to offer software for to run cloud infrastructure as a service providers. And Cloud Foundry promises to address the platform as a service space, which launched by VMware recently. So we're starting to see open source software that can actually be used to run the cloud, or open source design that can be actually used for this. So a few words on how the OpenStack project started. So on one hand, you have Rackspace hosting. Rackspace hosting runs the Rackspace cloud. It's an infrastructure as a service offer that has cloud servers for the compute part and cloud files for the storage part. So it was very successful. Cloud files was written in Python, so it scaled horizontally, so the success wasn't really so much of an issue. Cloud servers is starting to see its limits in its design, so they wanted to rewrite it in Python, and so that it would be horizontally scalable, and so that it can meet the needs of tomorrow. And they also, in parallel, decided in May 2010 to open source the software behind their infrastructure for the reasons I outlined above. On the other hand, you had NASA. NASA was building a US government private cloud for hosting government sites and do heavy calculation on like pictures of stars. And to overcome the limits of the software they were using, they started to rewrite their own cloud compute software in Python. And they released it in May 2010. They released an early version of it called Nova CC, written in Python and Apache licensed. Some people noticed the potential for convergence between the two projects. In particular, the architecture for the compute part was remarkably similar between the Rackspace project and what NASA had put out in the open. and both were written in Python. So they talked to each other and they decided to form a common project called OpenStack, where you would take the code from Nova CC for the compute part and the code from Cloud Files running in production at Rackspace for the storage part under the name Swift. The mission statement for the OpenStack project is to produce the ubiquitous open source cloud computing platform that will meet the needs of public and private cloud providers, regardless of size, by being simple to implement and massively scalable. So we did that. The project was founded on 4 basic principles. Open source. So it's Apache licensed, and we promise not to do open core or to have an enterprise edition that has all the interesting stuff. Everything is in the core, in the Apache license code. Open design, we do design summits every 6 months under the model of Ubuntu Design Summits. So everyone can come, everyone can submit blueprints for new ideas of features. We do open development, we do heavy use of distributed version control system. Anyone can propose a branch for merging in trunk, and we do the code reviews in the open as well. So you know why your code is not accepted or accepted. And we do open community. We have all the discussions in public channels. We have community elected technical leads for the project. We have community elected seats on the project board. It's very much under the model of the Apache Foundation for those who know about it. Slightly less open, but almost. One thing to keep in mind is that it's a very young project. It's been 1 year since it started. We had 3 design summits. We had 3 releases. So it's about 1 year now, I guess. It's a young project, but it attracted a lot of attention. There are about 100 developers now that have committed code to one of the core projects of OpenStack with well-known names. Those are not the usual picture of OpenStack partners, which are not people committing code, just people giving us a logo. These are people that have actually developers on payroll committing code, so that's the real ones. A few words on our design and coding standards. So scalability and elasticity are our main goals. Features that limit our goals must be optional. Everything should be asynchronous. Main components should be horizontally scalable. We should always use share nothing or sharding. We should distribute everything, especially logic, and move logic where state naturally exists. We should accept eventual consistency and embrace it where appropriate. We should test everything. It's unit tests, but also smoke tests that actually deploy the code in some test data center and run a real workload on it. And we enforce PEP 8 for code consistency, which is extremely important. So if you're interested in our continuous integration toolchain, I invite you to come to a Soren Hansen talk tomorrow at noon. We will go into more detail on how we ensure that those rules are followed before the code actually hits the trunk and get built into multiple packages. But there are multiple types of OpenStack projects. There are the core projects, which are the one we actually care about. There are 3 of them now: Nova for compute, Glance for handling disk images, Swift for storage, and I will go into more details on each of those in the next slides. We also have an incubation process that is very similar to the Apache Foundation incubation process. It's usually a project that we would like to have as core projects someday, but are not ready yet. So there is a common authentication framework that will be shared among all the core projects. There is a Django-based web UI called Dashboard, and we are also building a queue service for starting to address the platform as a service space under the name Burrow. Those are all Python projects. Our release cycle is time-based. We recently moved to a 6-month release cycle. We used to have 3 months release cycle, but it was a bit stressful for the release manager, so we moved to 6. And it's a 6-month release schedule with a consolidated release of all the projects at the same time. Most of the core projects are actually following a common release schedule, because we do 6 months release schedule with frequent milestone in between. So we have a tarball or a release built every 4 weeks that are development milestones, and the last development milestone, called Diablo 4, is extra QA'd and becomes the final release. We also have a more stable or independent project like Swift, who have their own independent release schedule, and they ask us just to include the latest version they had into the OpenStack common release. So let's go into more detail into what are those projects. Swift is the cloud storage part. It's object storage. It's not block storage, so you won't create a file system on it. So you just store and retrieve binary blobs. It does so through a RESTful interface. There is no object size limit except the size of your cloud. It's because we use segments and manifests, so you can upload multiple parts and then the manifest that ties them all together. It's stable and deployed in production as Rackspace cloud files, so you can test that it works correctly. And it scales massively, and I will explain why. So Swift has 3 levels of containers. There is the account, which is usually tied to your credit card. The container, which is like a folder, and you can store as many objects and as many containers as you want. And you have then a flat structure of objects that are accessed by name. Swift uses rings. Rings are distributed hash tables. So you basically partition the hashing space into smaller bits, and that allows you to map. Well, we'll see how we use them. This is an example of a ring with 8 partitions. So anything that hashed from 0 to 1 FFFFF falls into the first partition. As everyone know about DHTs already. Yes. Cool. So how does it work? When you store an object in Swift, you use a call like this: put /API version / the name of the account /container /object. And what Swift does is that it takes the account slash container slash object part, builds an MD5 sum out of it, looks up this MD5 sum onto the object string, and then it falls into one of the partition. And this partition is linked to a unique set of 3 servers. And that gives you the servers where the data will actually be stored. So the file is received by a proxy server. The proxy server looks up where the file should be stored on a local copy of the ring, and then stores the object into the 3 servers. The idea is to have those 3 servers in 3 separate zones. Zones can be like a switch or a rack or a data center based on how lucky you are. and that handles redundancy for you, so you don't have to have pricey object servers with crazy red cards or anything. This is what ensures redundancy. So that's pretty cool because it scales horizontally, but there is a problem. If you want to actually list the objects that are in a container, you don't have a central index that stores everything where everything is, because then it defeats the whole purpose of using rings. So that's where Swift uses a trick. It uses another ring. So to list objects in a container, you do get /API version /account /container. And what Swift does is that it takes account /container, turns it into an MD5 sum, looks it up on a separate ring called the containers ring, and finds the 3 servers that will actually contain the listing of your objects. And you do the same to list containers in an account, to get the list of containers in an account. So your deployment looks like this. You have proxy servers. Each of those have copies of the 3 rings. And you can have as many of them as you want, since you want to handle with the client load. And then you deploy object servers, container servers, and account servers in at least three separate zones. And it scales horizontally, and you can use commodity hardware, so it's cheap. You can use crappy disks. It works. There are a few other components. The account reaper actually looks up for dead accounts or people that don't pay, and removes all their objects. The updater actually takes care of when one server doesn't answer. There is a fallback server. That fallback server will use, the updater will use those fallback servers to copy the data back onto the server, the original server. And the auditors are crawling the object space, just making sure that random objects can still be accessed. That was Swift. Next project is Glance. So Glance is the image service. It's about discovering, registering, and retrieving disk images and associated metadata. So it's a very special service. It's much smaller than the others. It supports multiple disk formats. It supports multiple container formats. I won't go into details. Here is the architecture slide. So you have Glance API, which received the request from the clients. The clients are talking a RESTful API called the Glance API. We're providing a CLI tool called Glance, and also a Glance client Python library if you want to roll your own. But anything that actually speaks the REST Glance API is quite easy to write your own client for it. So Glance API received the request. It uses an internal RESTful API called the Registry API to query metadata information or location information about the disk images. So we provide one reference implementation of it called the Glance Registry, which has an SQL backend, but you're free to implement your own crazy NoSQL version of it, as long as it speaks the Registry API, which is a REST API with Glance API. And Glance API uses multiple storage backends where it actually stores the disk image, which is the large part. So it can use Swift, it can use Amazon S3, it can use a local file system that's useful for tests. And it can also use HTTP links, but that's only read-only. Then you would basically tell Glance where to fetch an image that is available over the internet. And you can combine them all. I mean, they're not exclusive. last but not least, cloud compute. So this is by far the largest. You can think of it as VMs being just one API call away. It's a highly modular framework, so you have to pick exactly the deployment options that you actually want to run. There are tons of hypervisors that we support. You basically don't want to support all of them at the same time. It's still under heavy development. We're still refactoring things, trying to separate things out. So it's not risky to use right now, but it's interesting to test. But for deployment, you better have a good IT management team. It's used in production in NASA Nebula Cloud currently, so it's working. And Rackspace Cloud Servers is expected to go using Nova before the end of the year, so needs to be ready. Those are the different components. So it's also a horizontally scalable componentized system. We have API nodes who are responsible for receiving client requests and acting on them. Scheduler nodes that actually decide where a given request will actually be done. A compute node that are responsible for the VMs themselves. So they spin up the VMs. Network nodes which provide network resources for compute nodes. And volume nodes which can contain block storage or interface with remote block storage. And all this is linked through a message queue. We use RabbitMQ. And you can have any number of those components that is actually needed to have your load. If you have a relatively low number of VMs, but a large number of API calls, then you should spin up more API nodes. If it's the other way around, better add compute nodes. So, for example, if you ask for a new server to be created, the client request would be received by the API node. The API node would put a message on the queue saying, well, this server should be created. A scheduler node, one scheduler node somewhere, would pick up the request and apply some internal algorithm to decide where it should be handled and put back a message on the queue to that compute node. That compute node will pick up the message on the queue, require disk images from Glance, and then ask the network node for network resources like, I don't know, IP addresses or networks or firewalls, and then would finally spin up the VM. And the API node, if the client queries for the location of his server, the system would point him to the compute node. So I said we should always share nothing, but unfortunately Nova shares a bit. We have a data store. we're trying to get rid of it, and it's hard to kill. So we're trying to move to shard as much information as we can among the different nodes and push as much information as we can into the queue rather than have a central data store lookup. It's an interesting project for those interested. A few words on modularity. I said it's a highly modular framework. So the API node is actually WSGI middleware, so you can stack up any authentication, whatever compressing stuff that you have. We support two APIs, the EC2 and the OpenStack API. So the EC2 API is widely used due to the success of Amazon Web Services. But we also provide our own OpenStack API. The reason for this is that we don't want to be stuck with what Amazon dictates the cloud is. We actually want to be part of it. So if we have a shiny new feature, we want to expose it to our users. And that's why we have the OpenStack API. We support multiple authentication plugins, database, LDAP, but that should be replaced by the Keystone project, which will have database and LDAP backends. That's the idea that you will be able to share tokens between the different OpenStack core projects. The scheduler node uses a pluggable algorithm. We provide two of them, Chance, which is basically round robin, and a zone-aware scheduler. I think there is a third one now. But it's just a matter of extending a class to provide your own logic. The queue is actually AMQP, any AMQP queue. It's not like tied to RabbitMQ. The data store, you can use SQLite for like development setup. MySQL, Postgres, network node, we support 3 network modes, IPv4 and IPv6. For the compute node, we support a large number of hypervisors. So QEMU, KVM, UML, LXC, Zen Server, Microsoft Hyper-V if you really want to, VMware vSphere, which is the same thing. And for volume nodes, we support local LVM volume groups, remote iSCSI storage, sheepdog volumes, and HP SANs. That's what I meant by lots of different options. You don't want to run everything at the same time. You have to pick based on your need. Coming up in the next release of Nova, we're actively simplifying Nova to separate some functionality out of it. So we're planned to separate the block storage service, the volume nodes that you've seen, so that they answer their own RESTful API, and that Nova would use it to call it. That's a project called Lunar, and we hope that it will be sufficiently complete so that it can be an option for Nova by September 22, which is the date of the release of this version. We also plan to separate network services. So we have a number of projects that have been spawned. Quantum that provides the network API that would be used by the cloud compute. So you could request an IP address, you could request an elastic IP address, you could request a network and connect them, and etc. Melange, which is a network resource registry, so like an IP address directory. And Donabe, which addresses complex network containers, so you can describe your network configuration and tell Donabe to actually make it happen with very intelligent switches. And finally, Keystone I already mentioned. So trying to have all those core projects use the same authentication mechanism. We also will have snapshot, clone, and boot from volumes, distributed scheduling, because we have the idea of zones now. We should hopefully complete the OpenStack API 1.1, and we should hopefully have configuration drives, which are like disks that are mounted on the VMs you spawn that contain data that the user provides. So that helps you communicate with your instance and customize it before it runs. Okay. Python. Why do we use Python? There was a good plenary talk on what makes Python awesome on Monday. What makes Python awesome for us, at least for me, is that our users are not end users, but are not really programmers either. So having a language that is easy to learn, that is easy to read, and easy to patch for sysadmins, that brings the users of our software are actually able to contribute patches back. And that's the main, I mean, for me, that's the main feature of Python that is relevant here. It's a community enabler. It's really useful to have a simple language that people can actually learn in 1 day or 1 week and start contributing bug fixes. But it's also because there are lots of very interesting libraries. So we're using libvirt, especially for having this weird collection of hypervisors. So libvirt provides for us the indirection layer that allows us to have those many hypervisors. For concurrency, we're using eventlet. So there was a big debate, Twisted versus eventlet, at one of our design summits. And we settled on eventlet, which was used by like half of the project, mostly because it's easier for someone that doesn't know anything about concurrency to use. While Twisted, you have to think the Twisted way. We use pest deploy for the WSGI configuration handling. We use webob to encapsulate response and request objects. We use routes for setting up, because we were lazy, to set up the REST endpoint. We're using Carrez to interact with the queue together with MQPlib. Apparently Carrez has been discontinued, so we probably need to move to Kombu now. We use SQL Alchemy for indirection at the data store layer in the 3 projects. And we use SQL Alchemy migrate to migrate the schema, the database schema from one version to another every time we change the schema. And as far as plumbing goes, we're using standard logging, standard HTTP lib, standard JSON. We're using Bodo to talk S3 with Amazon. We're using M2 Crypto for anything cryptographic. Nova is using G-flags for configuration files, but I think we are going to move away from that. So feel free to come and join the fun. It's a very open project. A few URLs for you. We are very active on IRC. So there is the OpenStack channel, which is more like a user of the software, and the OpenStack dev, where the development discussions happen. We have weekly team meetings on IRC, so it's a bit inconvenient for Europeans. It's like at 11 p.m. on Tuesdays, and we have a mailing list, a central mailing list for all our discussions. That's it. Questions?
Are there? Okay. Thank you. I saw OpenStack implements many Amazon and Rackspace feature at APIs level. What are the future plans for these different approaches?
Could you repeat your question?
Yes. I saw OpenStack implements many Amazon and Rackspace features at APIs level.
Yes.
The future plans for these different approaches, if you plan to bring on both or...
So the OpenStack 1.1 API is modeled after the Rackspace Cloud 1.0 API, and plus extra features that we have in OpenStack. So it's a superset, if you want. So we already support the Rackspace Cloud 1.0 API, I think, pretty completely. We're having a bit of trouble with the API because they are usually defined by other groups than the one that are actually working on the software. We need to fix that. As far as EC2 goes, it's a best effort to try to match the features in that EC2 provides. But obviously, Amazon is changing their API whenever they want, and they don't give advance notice to anyone about what that will be. So it's always late in some ways. Sometimes it's not very late. Sometimes it's completely late. Sometimes it's features that we won't support completely. But the idea is to support both APIs. We have, especially since we have now Ubuntu server that has picked OpenStack as their default cloud stack, and they care about the EC2 compatibility more than most of us do. So they're supposed to make sure that we are up to par with general EC2 compatibility. As an example, Eucalyptus that claims EC2 perfect compatibility is not perfect either, because they suffer from the same issue. They also have problems keeping up with Amazon. That answer your question?
Yes. Is there a milestone to improve the documentation part?
So documentation is actually quite good when the projects are stable, but it's difficult for we have technical writers and a community group that works with her. The problem is keeping up with the pace of changes. It's really going very fast. It's like thousands of commits in 1 month, and sometimes the time it takes for them to write the chapter, it's already obsolete. So it's definitely a concern, and there are teams now at Rackspace that sell training and provide good documentation. So I hope that it will be improved. But the software needs to calm down and slow down a bit if you want any documentation to be accurate. So Swift documentation is okay. The inline documentation and everything we generate by Sphinx is actually quite accurate. The PDF books are not that accurate, for Nova especially.
Oh, wait, really?
Stack is in the development part. In the APIs, often there are only the documentation defined in the procedure and functions.
The API is one of the things that are actually well documented. The OpenStack.
The Nova, in the Nova part.
In what? Sorry?
Nova. In the development part of Nova.
You mean the OpenStack API or?
Yes.
The OpenStack API is very well defined. The problem is, do we actually implement it correctly? So
correctly, but zipped. Very short.
Yeah, it can always be improved, and it's a community project. So if you're really interested in it, it's actually the best documentation came from outside of the developer group and the main companies.
Can I build a hybrid cloud using OpenStack?
Sorry?
Hybrid cloud. Can I build with OpenStack?
The relationship between libcloud?
No, hybrid clouds.
Hybrid clouds. So yeah, hybrid clouds. So you can use public clouds, you can use private clouds if you deploy them inside your firewall. And the idea behind hybrid clouds is that you can deploy half of it. Well, you can move your application from the private side to the public side, burst to the public cloud, etc. So OpenStack is an enabler of hybrid clouds because it's good to just say, well, you're C2 API compatible, but it's not enough because everyone has its own version of the EC2 API they are not similar. If OpenStack wins and becomes the Apache of the cloud, then you will have OpenStack clouds everywhere, and you can run your private cloud with exactly the same code as the Rackspace and others, and then it's like true compatibility. It's not just like, well, this API looks like it's the same and it looks like it's 99.9% correct. It's about running exactly the same code. So I hope that OpenStack will facilitate the emergence of hybrid clouds and make them, and the emergence of federation of clouds, of cloud markets, so that you can compare the prices and the services of each provider and drive the cost down and break Amazon's monopoly. That's my personal goal.
Hi. Before you said that you were using a mix of eventlet and twisted, and you're now focusing on eventlet. But I had a look at the source code for Nova, and they are both two things living together. Is there any plans to phase out
you mean there is
eventlet or twisted or?
Yeah, there is one component that I didn't mention in the architecture slide that is the Nova object store that still uses twisted for historical reason. No, it doesn't?
Not going to be phased out. Like for
Wait.
like a couple of months at least.
Ah.
At least a month. It's been a month. It doesn't use twisted anymore. The only dependency we have on twisted is like a couple of base classes that is still.
Yeah. Where did I start? Right, the object store does not use twisted anymore. The only twisted stuff that's left in the code base is really, I think it's a couple of base classes that we just happen to use from twisted that no one has really bothered to replace with, something not twisted so we can remove the dependency. because it's not, doing cool twisted-y sort of things. It's just using, I forget what it is. It might be like a log rotating thing, or just really not asynchronous related stuff. So no, we don't use twisted anymore. Maybe you looked at an old release, or.
Let's look at the latest one.
That's all.
Oh yeah, ancient. I mean, it's what? It's weeks old, isn't it? What, months even, maybe. I mean, time flies. You need to keep up.
That's what I meant by under heavy development.
Okay. I've seen using the rings, you can point to a disk resource. I mean, part of your storage coming from the account and the container, so you can point to the correct data you mean for your current virtual machine you are running in the moment. I've seen that you have, for instance, 3 times the same data in the slide, replicated 3 or a number of times of replicas of the same data. They are kept in any case current. You work with one single instance, and the other 2 are kept aligned with it. Also, I've seen that you declare you have no RAID or no redundancy on this data.
So
the last and how can you used to move data? The slide back, the previous one maybe. Yes, I mean this in this part of the next one.
Next is this.
Okay, this one for instance. So you can point it to zone A, zone B, or zone C according to the.
No, it's not or, it's and.
Is and. So in any case, you mount data from all of the 3 areas.
So So I pointed. So in each partition, the partition contains the names of the 3 servers that should contain your data. It actually also contains 2 additional servers, which are the fallback servers.
Okay, the fallback.
That's the one used when 1 or 2 of those servers don't answer, right? So you have 5 servers with 3 primary servers and the system makes sure that you have those 3 servers in at least 3 separate zones. This is configurable. You can have 6 or instead of 5.
A number of replica of the data, and they are kept aligned. In any case,
when the proxy server receives the put request, it actually puts the request asynchronously onto those 3 locations. It's not just one.
Okay.
And that's where the redundancy happens. It's why we don't really want to care about RAID, because that's just one aspect of redundancy. Like then there is power, then there is the OS that can just go boom or whatever. So we don't really care. What we want is store it in 3 separate places and
the first
handle
reply
redundancy like this.
Yeah, the fastest the replies is okay.
You could increase the global redundancy by setting all those on RAID servers, but the idea is to use cheap hardware rather than an expensive one. So better not rely on RAID and not degrade the performance of your system and store it in 3 different places. This is eventually consistent. It's not like atomic commits or whatever. It stores when it can, and then when you retrieve the data, you might get, if you do it very, very fast, the previous version.
Okay. And in this case, the supervisor of the old storage can define where the data storage are kept in which country. I mean, in Italy we have some laws about keeping data in the United Union, for instance, so you can define that your object server B should, or all your object server for a specific customer must be located in a country.
So
that's why Italian Telecom is suggesting their own cloud.
That's new features for Swift. I know they plan to add that, to add like geographic aware type of queries. Currently, it's tailored to the needs of Rackspace Cloud. So it's like a unique thing that is running in the US or a unique thing that is running in the UK. They're completely separate. So they don't really care about geography zones like Amazon does. But they want to have a pluggable way of storing things, so that you could use a Gluster backend if you want to, or others. So I know that, and they want to support geographic queries. The ring is a bit more complex than I showed, obviously, because it's weighted. So the size of your partition depends on if you have larger servers. Obviously, you want them to store more data. So it's a bit weighted. And there is an offline tool to generate those, and it's idempotent. The tool can be generated on all those API servers and will return the same rings in the end. So whenever you add servers, obviously some partitions get split in two based on their current level of use. There is lots of smart things done by the Swift ring builder to ensure that you get the optimal spread of your data, but it's a bit more complex than just splitting the hash space in 8 partitions. Pass.
Other question? Hi. So I have a question for the ring. Maybe I missed something, but if you split the ring partition into two, and there is a new server. You had one server. Now you have two. You have to move the files from this old server, couple of the files, to the new server, right?
Yes.
Okay, that's why I wanted to make sure that how you
so.
do it.
So I don't know if it's the updater that does it or. What? Oh, one dead. I don't know if it's the updater that does it or the new the servers in the new partition that use rsync to get them from the previous servers. I can find out for you. I'm not a Swift developer or a developer for the matter, so I just learned enough to make those slides and appear smart. It's a lot of projects. It's a bit difficult to keep up with all of those. I'm mostly following Nova, to be honest. So.
Right, so it's really modular, I see, OpenStack. It's really modular. There is a lot of different projects.
Yes.
And is it made to be introduced progressively into an existing infrastructure?
So you don't have to install all of them. I mean, Swift is completely separate from the rest of the core projects. Glance and Nova work together. Burrow will probably work with Nova as well as the infrastructure layer below it. The Keystone thing is linking all of those, but you don't have to deploy everything. I mean, Nova is standalone. You can even spare Glance. The Swift is standalone. We will have more and more projects, so we ensure that they work well together, but that doesn't mean you need to install everything to make like an OpenStack cloud. You just provide the cloud compute part, you provide the others.
Can you talk a bit what kind of projects you currently have in the incubator and what kind of projects would you like to see?
So incubation, we have. It's a bit of a fake slide because we don't have so many incubated. The incubation process has been like decided 1 week ago or 2 weeks ago, so it's what I would like to see personally. So Dashboard was officially voted an OpenStack incubated project Tuesday. Keystone is as applied, but we did. Oh no, it's accepted too. Keystone is accepted too. Burrow is expected to apply for soon. We had other projects that applied that got rejected, at least temporarily. What will we have here? At that point, I think it's the only 3 projects that I think should be core projects for the next release. The idea is that you are incubating for one release cycle, and then the next release cycle, you're part of the core project. So we need to make sure that they're up to par for our release management process, that they're sufficiently present on IRC so that we can communicate with them, that they're sufficiently integrated with the way things work so that we can actually work with them as a core project. And there are lots of related projects. I didn't talk about them. It's things that will never be in core, like mobile phone clients or deployment tools that well, there are like 10 of them. We don't really want to choose between those. They are all working with OpenStack or OpenStack compatible. They could have a sticker, but I don't think they should be made core projects of OpenStack. For your question?
Is Glance meant just to store read-only disk images or also modifiable one? I'm thinking the difference between a CD-ROM image and a virtual machine disk snapshot.
It's meant to store. I think it's meant to store the base images that the compute service will offer as an option. So like you want Ubuntu server 10.04 LTS, then the Glance service can allow you to search the base for all those that are compatible with that, and with the RAM the RAM and CPU options that you want, and retrieve that disk image. And we also push the idea of rather than rebundling, to do boot time configuration. That's what Ubuntu does with their Ubuntu Cloud images. So you have a common image and you boot it with specific parameters that actually configures it into something that does something relevant. And I think it's better than the rebundling stuff where you need to upload. That's how Amazon does it. You need to rebundle your image and upload it again to S3, store it there, and that's a slightly different approach. I don't see why Glance could not be used to store like snapshots or.
It does.
It does. Oh, fuck.
Yeah, when you create a snapshot, it ends up in Glance. That's how it works.
Not the log storage one. The boot from volumes is separate snapshots. Then.
Oh, that. Yeah, good.
And we have.
I think it must be the OpenStack API that has an API call to create a snapshot of a running virtual machine, and that ends up in Glance. That's where it extracts it and puts it into Glance.
We're adding in the new version the possibility to snapshot, clone, and boot from volumes. So that's a block storage that is handled by the volume API. So that's one option, but you can also snapshot disk images and then push them to Glance and boot from that instead. So it's, like I said, lots of options. Sometimes difficult to tell which option is the best combination for your use case. We expect that the Ubuntu guys will come up with like a standard Ubuntu-centric way of selection of components that makes sense altogether to deploy a private cloud, because that's their target. And that will be easier for people to test. You can actually deploy all the components on a single machine and run with the local RabbitMQ and SQLite databases and test everything on a single machine, which is very useful. It scales up but also down. So it's not that difficult to evaluate.
Just last quick question.
Actually, I have 2 questions. Too bad. First question is, how long is it going to take before we use OpenStack in production?
Well, it depends on your definition of. It's already, all the components are already used in production. So except Glance maybe. I don't know, who knows. So Swift is used in production for Rackspace cloud files. And so it's like, it's the code. Like we released the version on Monday and it's already deployed on Rackspace Cloud in production. So this is very much production ready. Nova is running in production at NASA to power the Nebula cloud that they use for calculation, but also to host various websites like whitehouse.org. And so it works. The question is you have to pick the most stable components. You have to have a good crew of sysadmins to keep up with what you should upgrade to, what you shouldn't, to provide the glue when the migration is not that easy from one version to another. So it's tricky to deploy currently to have Nova in production, like with a small group of IT guys. You can definitely test it. You should test it to make sure that it works for your workload. It's the best way to ensure that it will meet your needs of tomorrow. Deploying today in production with a small IT service and in a private enterprise to serve users, it's a bit risky. I expect it to stabilize in 6 months once we separate all those APIs. I think that the migration from the current version to the next version where we have those API separated and the new services are fully replacing the old ones, I think the migration path would be a bit bumpy. And maybe that's...
Okay, thank you very much, Thierry.